let us look at exercise 1 from chapter 6, um, where we consider the case where we have just one policy. So consider, for example, Johnny, and we're looking at the heterogeneity model, which basically means you use one heterogeneity parameter theta to characterize certain aspects of Johnny's policy, and um, we have one claim number x. We assume there is only one observation here, and this x uh, given theta is Poisson distributed with mean value theta, where we assume that theta is some heterogeneity parameter, which is a positive random variable. We also assume about theta that it has first moment, second moment, third moment, and fourth moment, and they're denoted M1, M2, M3, M4. Now, since we assume that x given theta is Poisson distributed, that also means that the mean of x given theta and the variance of x given theta are equal to each other, and they are both equal to theta based on the Poisson distribution assumption. We are asked then to find a linear Bayes estimator for the expected value of the claim number given theta. Now, normally we denote this thing using mu of theta, right? And normally we will denote its estimator using mu LB hat, where hat stands for estimator and LB stands for linear Bayes. However, we have just established that since x given theta is Poisson distributed, what we do in this case is then this expected claim number will be equal to theta. So essentially what we need to do is to estimate theta. So the linear Bayes estimator will just be denoted theta hat here. And then afterwards, we're also asked to find the minimal linear Bayes risk rho of theta hat. Now, one of the things that we can do, there are kind of two ways to solve this exercise, and I will present both ways. The first way uses the formula for linear Bayes estimator in the Bühlmann model. And the reason why we can use the formula for linear Bayes estimator from the Bühlmann model is that since the assumptions of the heterogeneity model are satisfied, then the assumptions of the Bühlmann model are also satisfied. Because if we let this denote the set of things that satisfy the heterogeneity model, then it is actually included in the set of stuff that satisfies the Bühlmann model, because the Bühlmann model is essentially a relaxation of the heterogeneity model, which is also the reason why we do linear Bayes estimation in the Bühlmann model and we do a more precise Bayes estimation in the heterogeneity model. So we can use the Bühlmann model to find the linear Bayes estimator here, and that is what we will do first. Now that is not the route they take in the PDF solution, so I will also demonstrate what they do in the PDF solution in the next video. Now let's just take a look at theorem 642 and try to understand what it's actually telling us. What it's actually telling us is this. It says if you want to find the linear Bayes estimator based on data x xi1 up to xi and I for the ith policy. So we're not exactly looking at the exercise now, we're just looking at this notation in general. So if you're looking at the ith policy, you have ni data points and you want to find a good estimator in a linear form of what you expect the claim xi to be given theta I. If you want to estimate that using a linear Bayes estimator, then the way you do that is by calculating 1 minus w multiplied by mu plus w multiplied by the average of these xi1 up to xi and I. Now, what does this actually mean? Well, it means this. Consider a policy where you have these claims. Now, essentially, I can draw up a table where I don't just have one policy, where I have, for example, three policies, right? And the way we look at this in chapter 5 and 6 is we have data for multiple time periods, t equal to 1, 2, 3, 4, 5, 6, and so on. And then we kind of have the data, x11, x12, and so on and so on. Now let's try to consider this one policy here compared to this policy that is over here. The thing is, for example, if I have a customer who's only been with us for 2 periods of time, and I have another customer who's been with us for over 6 periods of time, then I can kind of say that the data for this customer tells me more than the data for this customer. And the thing that linear Bayes estimation does, essentially we call this thing the credibility estimator. Credibility estimator. And the reason why we do that is because it tells us if you want to estimate for a given policy the expected claim size given its theta parameter, then the way you do this is by, first of all, taking the average of observations in this column, and then you multiply that by a weight. Secondly, the thing you will do is you take the average of observations for the entire portfolio and you multiply this average by another weight. The thing that happens here is you kind of say, depending on how many observations I have for one given policy, then this weight will either give the policy average a higher importance or the portfolio average a higher importance. So the mu stands for the portfolio average, and the xi bar is the policy average. And it is something that we can kind of interpret by looking at the construction of W. So W is given as Ni multiplied by lambda divided by phi plus Ni multiplied by lambda. Now the Ni is the number of observations for policy I. So if I'm looking at a policy, for example, this one here, where there are a lot of observations, then this term divided by this term is basically 1. Or this term divided by the entire term down here is basically 1 if the Ni lambda dominates over phi. And in that case, the term with the policy average will dominate my estimate. However, on the other hand, if I'm looking, for example, at a policy here where there are only 2 observations, for example, then the phi will dominate over the Ni. And then what I essentially do is I put more credibility in my portfolio average. And there's also a funny thing kind of with the phi construction, because if we look at how phi is defined, it's the mean value of the variance of x given of the variance of x of actually x whatever given theta given theta I. These variances, they are IID because the thetas are IID. Now, essentially what the phi more or less stands for, we can interpret it as a portfolio-wise variance in claim size. So if there is a great variance in how the x's look, then you will need a higher number of observations for a given policy in order for the policy average to be more credible. So this W is actually constructed in a way that is completely intuitively reasonable. So this is what the linear Bayes estimator how you can interpret it. Now it consists of the lambda, the phi, and the mu, and we will need some expressions to calculate it. So I've also written them up here. And also what I've written up here is the minimal linear Bayes risk phi of, not phi rho of the linear Bayes estimator, which is calculated as such. So that was a little bit of intuition on the general linear Bayes estimator in the Bühlmann model. In the next video, we will actually start calculating this for exercise 1.